That's original video where we have several tasks. Task is to get the red ball. So this task is specified as there are two objects, a right hand gripper here and the red ball. They are have to be connected, then the task is fulfilled. So there are two representations about the world, the facts and kinematic. Kinematic means joints angles of the robot. Multi-level architecture where you have knowledge represented in two different forms, and these forms are connected in this approach.
The approach itself doesn't involve learning. It's a computational-based approach, so that finds the most optimal solution. And in order to search for a solution, we need some representation of information about the world. All you see here is just a kinematic trajectories optimization. So there is no real contact going on in this simulation. So these are videos made at different steps of optimization process. So at the very beginning, you see no optimization process done so far, and in this case, optimization process is counted by Newton steps, which are shown here. So in Newton, it's step 0 means it's before optimization starts. Then, after we did a few Newton steps, you can see that the approach can find a certain solution, but the objects are floating. So maybe that will give you some intuitive understanding of what I'm saying. There is no real dynamics. It's kinematic representation. And after a maximum number of optimization steps is done, what you can see on the bottom right, it looks like real physical interactions. But in reality, it's just a process of optimization going from left to right in the upper row, and then from left to right in the lower row. So you can see here Newton step 0, Newton step 3, Newton steps 15, and Newton steps 1000, which means just the maximum number of steps. The goal was just to get the ball, but the problem is that it's not reachable by stretching out one of the arms. And moreover, at the very beginning, configuration of the object in this problem is in such a way that robot even cannot reach the bigger stick. So it's the only thing that it can reach right now on the table is the small stick. And then with the small stick, it's possible to get closer to the bigger stick, and then with the bigger stick, it's possible to reach the red ball. It's not possible at the very beginning to grasp the red ball. Therefore, we have to use tools to grasp the red ball. In this case, the actions that you see on the upper left corner, they, at the very beginning, we assume that they can happen in the environment, and therefore we put magically all the objects in relative attaching position in the environment. But at the end of the optimization process, everything has a cost function, and therefore this huge jumps would have very high cost. And by optimizing the cost function, we have a smooth translation in the environment, which seems very natural. So here we have approximately 35 time steps, and the time steps are denoted on the upper left corner. And below that, you see actions which were executed, and the actions involve grasp. Next action was push, then next action was place, then grasp again, then push, and then grasp. And this sequence of action was found in a symbolic search. First action is grasp stick 2. It's in this case it's a small stick with backstar R. It's right gripper of the robot. For this step we have 5 time steps. So for each and every action in this optimization process, in this case we have 5 time steps, because we specified that as a parameter of our optimization in the upper right corner steps per phase. So in this case, we call these actions a phase. Therefore, we have 5 time steps for each phase. We have 5 time steps to initialize the process. Then the next 5 time steps comes to the grasp action. Next 5 time steps go to push one stick with another stick on a table. Next 5 time steps pushing process. Then placing, we place with a red gripper stick number 2, which is a small stick, on the table 1. And for the next 5 time steps, that's what's happening. This small stick is being placed on the table. Next action is grasp with a left gripper stick. In this case, stick means the bigger stick. That's what's happening in the next 5 time steps. And then the action push, red ball using stick tip over table 1. And then grasp Baxter R, red ball. So how does it look like before optimization process? So as you can mention, these are the same time steps, which are sliding on the left up corner. And now you see that objects just appears and disappears at different places in the environment. And that's because each action is changing some facts about the world. And these facts are in the sense that if we have action grasp, stick 2, then we assume that the action can be executed, and we just put stick 2 attached to Baxter R gripper. And the same for all other objects. Each action, it has predefined influence onto the environment. And this predefined influence, like attaching objects, grasp action, in reality attaches these two objects to each other. And push and place objects, they also have predefined functionality. And this predefined functionality usually uses basic translation and orientation values, like 0, and therefore you just see such jumps. But after that, we can run the optimization process. That optimizes the trajectory, and then this looks much smoother.
So these are some decision rules which are handcrafted. You apply all of them to the given state of the world, because this is extensive search. All of these rules are applied. For example, heat slide. Maybe it doesn't make sense, but you just apply, and you hope that later, in the next level of leaps, there will be state that would allow to produce quit instance. So, for example, heat slide maybe doesn't matter at all in this situation, but you just apply and change logical representation about the world, and then you do it again until you find a logical solution that after some levels you are able to grasp red ball with left arm. And then, even though you logically found this solution, you still have to check validity via kinematic optimization.
So on the left side, you see facts about the world which we have before the action is applied. Then we have a decision rule, and decision rule, it's kind of general class for an action based on action grasp. But now what we can do, we can put different objects for grasp. It could be, for example, Baxter R and stick. And what this decision rule is doing, it has some preconditions which is being checked in the pre-state. So, for example, gripper X. So X object should be a gripper. It should not be a table, or it should not be an object. It should be a gripper. And Y variable in this equation shouldn't be an object. So it cannot be object type table. It cannot be object type robot. It can be object type object, which are, if you remember, if you can see here, objects are stick and ball in our environment. So if you found two objects, like one gripper and the second is object in our pre-state, and the gripper X is not busy, and the object Y is not held, then we found an entry for our decision rule. And now we can put entities, like real entities. In this case, we selected Baxter R and stick. So we checked all these preconditions. We found a set, and now we can put some real object inside. So, and this decision rule is possible. It's represented by this node here. So grasp, Baxter R, stick, and you can see that with this decision rule, simple decision rule, we can create different possible actions. We can create action grasp Baxter R red ball. So just by changing here object from stick to ball, that's the ball, and applying just one decision rule for the same pre-state representation of the environment, we can create two different actions, although they are both based on the same decision rule. And if you look further, you will find out that what we do here, we just iterate through all possibilities. So it's the same graph. We have Baxter R, Baxter R, Baxter R, Baxter R. And here we iterate through all possible objects to grasp. And then when all possible objects are over, but in our case, we have only 5 objects on the table. 2 of them are kind of belonging to the same object, because stick 2 and stick tip 2 it's just 2 different locations on the same stick. But anyway, when all possibilities are over, we continue with the next. We just switch to our left arm and start to iterate again through objects available in the scene. Red ball, stick, and so on. And that's just a small patch of the huge tree that you saw in the previous slides. That's what we can do with decision rule. We can roll out decision rule into possible actions. And now these actions, they affect the world. And by affecting the world, I mean they change the state of the world. So they create, for example, right hand became busy, and it was not busy before. And ball became held, it was not held before. And it also added some other interesting things to the post state, for example, comma. Comma now it's our connection to the kinematic world. This creates a cost function that ball should be inside of a gripper. Here we come to the cost function, which I will cover in some of the further slides. And these are possible decision rules in the approach. It's grasp, hand over, place, throw, hit slide. So hit slide, it means that we have additional attachment to object type table. Push, grasp slide, and here you see we always have some additional object to be attached, probably some more than just a table. So we have slide alone and drop. All these decision rules are capable of creation of action nodes based on this possible input object type. And that's how you create this tree search. And as I mentioned, that just the first percent of the tree, which in our case extends to, so you can imagine, and now this all leaves, they can expand. So now you can imagine how huge the tree is.
Each error, each decision rule changes the state of the world. Therefore, let's say this is our state of the world. We have about 10 or 20 decision rules. We apply them, and we have, as a result, let's say 10 new states of the world. There is a set of decision rules. They are handcrafted. There's a written function. Those decision rules, they change specific features in the state. So in this approach, of course, this is, as you can see, it's branching a lot. We, of course, can have kind of randomly generate decision rules. In this approach, it wouldn't work. So it's a handcrafted set of decision rules. A single decision rule can handle grasping of a ball, of a stick, of a table, of anything what is graspable. So this approach so far is kinematic. That means that even it penetrates the table, it can still solve the task. So if you would play with the simulator, you will see that sometimes the robot decides just to cross the arms, and the arms goes through each other. So there is no physical constraints. Although you can generate such a fact in your imaginary decision rule, so the precondition for decision rule is satisfied. For example, a red ball is free, and gripper is also free, so it's possible to grasp. You ask the system, is readable free? It tells you yes. Is my manipulator tree free? It says you yes. Okay, you say grasp ball with manipulator. And then we have kinematic limitations. So those kinematic limitations is, for example, you cannot grasp something that is far away from your manipulator. So your manipulator has a certain length. It's not stretchable. We have to check that.
So as you can see here, we check for the solutions, right? And here we involve kinematics. And here on the left side upper corner, you see that these are kinematics for each action. And for some actions, there is no kinematic possible, because we, for example, cannot control stick tip 2 right now. But as soon as we can control something with Baxter R, we execute that. And if we find that something is feasible, for example, it's feasible now to grasp stick 2, we proceed from this state, optimizing our second state, state that we get after the second action. Each action, it changes the facts of the world, as well as it builds additional cost term in the global cost function, which we are trying to minimize. There is no learning involved. Here we just do a search in a tree and then do optimization in trajectory space. With that, we do not have any priors for which way in the tree is better.
What they're doing basically, for example, you have a decision rule which is valid, grasp with left hand red ball, and then you have a loss. Loss is a distance, and then you can start to optimize your joints, joint values, your angles. You can differentiate how should you change each joint value. So here there are like 1, 2, 3, 4, 5, 6, maybe 5, 6 joints, and each of them is a angle value. Gripper comes close and close to red ball. But anyway, there is a limit of this optimization, because no matter what angle you specify, you will never will be able to minimize this loss. There anyway will be a huge distance. And it's not possible to optimize it any further, and the loss is still huge. So we say that although the decision rule, the action grasp red ball valid, but it's not kinematically valid. As it's not kinematically valid, this decision rule, we just truncate them, because all other decision rules are not valid, because this one is kinematically not valid. You did this and you changed your state of the world in this leaf, and you can do further planning by thinking that you have already grasped the red ball. But when you start to check it kinematically, your decision to grasp, you realize it's not feasible, and then all other decisions based on this new state of the world are not valid anymore. Therefore, you truncate them, and you do not proceed that anymore. But you also check the kinematic validity of other actions on the same level. And those which are feasible, you proceed with them to enroll them. So first with some logical decision rules, and then you check those logical decision rules, you check them for kinematic validity. And you do that until you get the state quit. So quit is also inside a world dictionary. And this quit is also produced by a decision rule. And this decision rule is a task of the environment. So one of the decision rules represents the task of the environment. So grasp, I guess, Baxter L, red ball. And as soon as you can do that, you have quit pointer and you say it's finished. And of course, the first actions that you would do, you would just grasp. But so you remember, we truncate those which are not kinematically feasible. Therefore, this action to grasp red ball is not feasible, and therefore you have to proceed to find the path that is kinematically feasible through other leaves, which in this case would result into grasp small stick, push big stick, grasp big stick, push ball, grasp ball. And this is just a bypass, because this straightforward solution would be just to grasp. But it was kinematically not feasible, therefore you have to search that path to satisfy the decision rule kinematically through other leaves.
I will not get into details about optimization of the tree search process, but you may assume it's just a tree search. So on the left side, you see the first 1% of tree search. So it was not possible to visualize a full tree search, but it just the most left image. It's just about 1% of the initial tree search, and then 99% comes later. When we just stopped tree search after 1% is done, that's what we got. We've got this structure. And if we look closer, you see here kind of my attempt to zoom in. If we go closer, we can recognize now that there are some green, white, blue, purple blocks, and we can discuss them in more details. In the root state, we have initial initialization, all joint values and positions. For the problem, we have initial position of the robot, joints, and objects in the environment. And that's represented by this green root node. Then what happens next, we try to apply actions. For example, these are all possible combinations, and then after applying one possible action, we can expand it to the next possible combination. And what happens there is, this is the root, that what you saw as a green node, that's the root. Then we have such a concept as a state of the world, which means it's the number of facts about the world. And the facts, they're saved in a list structure, where we just namely have description of objects which are available and states and processes which are available in the environment. So instance of table desk, we have object and instance of an object ball stick. We have a gripper, or an instance of the gripper Baxter R. So that means these types of entities, they have some predefined properties, and instances, they share these properties. We also have such flags like Baxter R is a gripper, and it can be as a if it holds already something, it can be busy. Both grippers are not busy. We can also check whether flags whether the ball is on a desk, or stick is on a desk, or whether ball is held or not held, and the same to other objects, like logical representation about the world. So we have these facts. And just now knowing these facts, we can apply actions. And actions, so what they do, each action is they change the state of the world. In this case, we have an action grasp, stick with Baxter R. And what it does this change the state of the world. For example, it changes from not busy to busy. And about the stick on the desk, at the beginning, before the grasp, it was on the desk, and after the grasp, it is not on the desk already. And the same about the held flag. So this red arrow represents respective facts about the world which are being changed by this action. And when we change these facts about the world, we can apply next action. And this next action also changes some of the facts about the world. And we proceed with these actions until we find a quit flag. And quit flag means that the task is solved, or potentially solved, because we right now solving the task just in the logical world, which means it can be a logical solution available. So if we grasp sticks and push a ball and then logically imaginary grasp the ball, that will be a solution, and we will get the quit signal flag. But in reality, this logical set sequence of actions may not bring us to the kinematic solution. Therefore, we have all this branching of the trees. Now we have to check all possible logical solutions, whether it's feasible or not in the kinematic world. So that's the connection between the logical world and the real kinematic world. So now we have to check this feasibility. So how do we check the feasibility? Basically, just run a short optimization process for each logical step, for each logical action. It's just a short optimization process, and some of the actions, so you can see here that the actions are changing, and for each action we try to execute optimizer, which minimizes the cost, for example, distance between objects. And now you can see here already these are two sequential actions. So first we execute one action and second action, and now we see whether the result of the second action is feasible. And in this case, it's a grasp red ball with left gripper of the robot. It's not feasible, so there is a certain threshold. If the distance is higher than this threshold, then the task is being not solved. But the first action was executed successfully. As the first action was to grasp stick 2, which is a small stick, on the table with right hand, and that's feasible. First of all, there is such a variable like environment, and in this environmental variable, all information about all joints and objects is stored. So you can always access information about position, orientation, angles. But now the question, what information do we need for our optimization process? And this information we select based on the actions that we selected. So initially, for now, our optimization problem, we need all the joint values of the robot itself. So that's provided by default. And then when we execute action grasp, slide, Baxter R, stick 2, table 1, this action already is bounded to information about stick 2, to information about Baxter R, and I guess some other, maybe a few more variables. So for example, stick 2 would add 7 values to the configuration space that we are optimizing. So in this task, we are optimizing configuration space, which means that if the robot has, let's say, 14 degrees of freedom, then what we do in reality, we optimize this vector of 14 values. And if we add to our equation the action which involves stick 2, like in this first action, then this stick 2 has also 7 degrees of freedom, position and orientation, and we add these 7 degrees of freedom to our configuration space. So now the dimensionality of our configuration space will be like 22 or 21. There is one more. So by having a stack of actions, we create our configuration space that we are going to optimize. We have also bounded to this action, we have cost functions. So for example, because there is a red ball involved in the second action, the red ball is the target of this action. So this action means a grasp slide with a tool Baxter L, object red ball. So the action itself implies that the distance between object left hand and object red ball should be 0. So we optimize, therefore we automatically create this cost function, and we now can run, in this case, Newton methods, which is just a second derivative gradient. We can run this optimization, and our configuration space is, in this case, about 21 values. So in this configuration space, you change them slightly in such a way that you minimize the cost, and the cost, which is created by this action grasp red ball, is based on the distance between gripper and red ball. So 14 of them are related to the robot itself, and then 7 are related to the stick, and in this case the smaller stick. 3 for position and 4 for quaternion orientation. That's what our configuration space look like. I'm just moving between labels and values. This is initial phase. So in the initial phase we have 5 time steps per phase, but in the initial and the final phase we have some wide deviating number of time steps. So in the initial phase, what you have, our problem consists of the configuration space of the robot. So these are joints, let's say right S0, joint between base and right upper shoulder. So these are all joints, and they are listed here. So they have values, and what we do, that's already the solution. this angle of certain joint changes over time, as you can see. That's basically the solution, because it just means if you feed these joint values and position and orientation values to the environment, you will get just these pictures. So different phases have a different number of values, because values that we would like to take into account, they're constructed by these actions. So each of them extends our configuration space. So at the very beginning, we consider only joint values of the agent itself, but the more tools we use, the more values in the configuration space we take into consideration. At the top, you see the phase, which is equal to action, and each action in this implementation has 5 time steps, but as I mentioned, it could be 10, 50, 2 time steps, or 3 time steps, as many as you specified, for the smoothness of the trajectories that you would like to find. Let's take a look one more time to the labels. These values belong to the stick, because we grasp the stick. The first 3 values, it's position, I suppose relative position, and the last 4 values are quaternion of orientation of the stick. Then if you move further, for the push, we have some slider object. You could notice in the videos that there is some gray and red sticks attached to the table, kind of slider, so that's the slider. When we have 2 sticks, we have then these values for stick and stick 2, and for the stick 2 it's somehow spread around, but this file is made automatically based on the provided actions. And our values about the robots, they are some floating somewhere here. Our problem is to optimize these values. And after optimization, you can just read this value and feed them to the environment, and you will get this visualization of a smooth moving agent. And the last one, that's the cost function. Again, we can see here time steps at each column. It's a time step. But now, instead of configuration space that we take into account after each action, we have the same actions as you see on top of this table. But now, instead of collecting values in the configuration space, we collect costs. And these costs, for example, that's a magnification of this table. So what you can see here is the values which we will use for the cost later. So these are values of difference between angles of the robot initial position and given position of in any time step. I was talking about homing. That means that if we have no other costs, the agent would just try to minimize this cost function to bring the robot to the initial position all the time. So as soon as we have no more tasks, then the robot will have to move back to the original position, and for that we have these difference values between current joint angles and original joint angles which the robot had at the very beginning. This is acceleration for each joint angle, and we use these values again for minimization, and this belongs to the f function. We are taking squares out of these values, and that would produce a cost scalar, and we sum them up. Homing task mapping and acceleration. And acceleration, we would like to minimize the acceleration to generate a smooth path. And as you can see, to build up a cost, we have to all time steps of the video. The agent always has some additional cost for being not in the original position. But this cost is probably small relative to the other costs, therefore it's okay to have some additional cost for home position. For example, here we can see in these time steps, we can see acceleration for new virtual joint. It starts after 2 time steps of the grasp, because to find the acceleration value we need 3 time steps, therefore we add this cost only after 3 time steps, as the stick 2 is already being attached to the gripper. That's cost for switching an object. When we do attachment, we would like to have 0 velocity as the attachment, and that's, for example, that could be a very huge cost in the not optimized solution. We can minimize this cost by changing angular values of the robot joints. Quaternion normalization cost. There is a cost for attachment. So attachment between stick 2 and Baxter R is the beginning of optimization. For example, here when the optimization is not fully implemented, we can have some distance between attached objects. So although object stick is attached to the gripper, there is a huge gap in between. And this gap will resolve into a big cost function for the cost of being inside a box. So we have some small box around the gripper, and our object stick should be inside this box. Then we have no cost, and if we have some distance, then we increase our costs. And by doing optimization, we change joint angles and positions and orientation of the stick in such a way that it becomes close to each other. So one thing that you should realize about this is that all these values, they will be processed one more time, like squared, or there are some other type of equations what to do with these values. But at the end, you sum up everything, all these values, and you have a single number for all time steps, for all different costs. So you just create a sum of all these costs of all time steps, and then by changing these individual values in different cells of this table, you can make this cost lower or higher. And then we just optimize step by step all this value in such a way that overall costs drop down, and that's how we come from jumps to a smooth trajectory. Because smooth trajectory will result in a smaller cost, mostly because we have here a lot of acceleration and velocity constraints. And also they have some different coefficients. So some of these values will produce higher cost and other smaller costs. So this table of cost is being created automatically based on objects in the environment and based on the actions that you provide. So all these actions, they have function which builds up the configuration space and which builds up the cost table. And this optimization is based on initially on the logical solution. So first we find this sequence in a symbolic representation and then translate that into kinematic representation, and then build cost on this kinematic representation and then optimize it in the kinematic trajectories. That's, for example, a snippet of a code where you build up this cost, calculate a square of what was of the values that was provided, and this values is one of these values from the table. So if it's a type of cost sum of square, we add this sum here. If there is other type of cost, let's say inside the box, we add to that in slightly different equation. Maybe one more thing to mention is that the value, gradient, and Hessian are calculated here as a functions. So we do not actually calculate the gradients itself. We just know what is the gradient in each point in the configuration space, because we also build up the equations for each point in configuration space. We know the gradient and we know the Hessian, because these equations are simple, so it's square of a value, and then we just build up gradient 2 times the value, and then we build up a Hessian. Here is just 2. So here square translates to 2 times the value, and now we have only the coefficient 2. And with that, we know exact value, exact gradient, and exact Hessian for each point in the configuration space. And that's how the costs of different terms look like. So these are our 35 time steps. Now we see that the green is acceleration. So that's acceleration cost. So when we approach in the end of the phase, we always have the high acceleration. And in the middle of the phase, we have a low acceleration usually. This black one is it's alignment of stick flip 2 and slider 1B. It's a connection of 2 phases and probably alignment of 2 objects, which was necessary for pushing. It was not good at the very beginning, but we can tolerate that because this peak in only 1 time step, and that means that probably it's somewhere here. Even though these values can be huge, in overall sum up of the full table, it's going to be like less than if you would have to change angular values for more number of time steps. And the purple is stick deep position relative to the world. So the proposed method is a planner. It's not a framework for executing such plans. And in the first level, it searches for a symbolic sequence of states that can bring us to the solution. And in the second level, it assesses the feasibility of the proposed logical sequence of actions and optimizes in the kinematic world.